In this video, I'm going to do some examples of simple antiderivatives. So first, let's do one using the antiderivative power rule. So suppose we have big F of x equals the indefinite integral of x to the fifth dx. So that means that we're looking for an antiderivative of x to the fifth. Okay. Now, there's a couple of different ways to do this. One way to do this is to look up the antiderivative power rule. Do you remember what this is? It's 1 over m plus 1 times x to the m plus 1. And I'll leave out the plus c for now. Okay, we want to use the antiderivative power rule here with a power m equal 5. Okay. So let's write this out. I need 1 over m plus 1, so that's 1 over 5 plus 1, times x to the power m plus 1. So that's 5 plus 1. And here I will write the plus c. At this point, we should clean things up a little and get big F of x is 1/6 x to the 6th plus c. Now it's easy to check that this is correct. So let's check. Remember that the antiderivative of a function is a function whose derivative is the thing you started with. So we want to find out if big F prime is x to the fifth. Okay. Well, f prime of x is, okay, well, the plus c won't contribute anything, but we have 1/6 times some stuff, so we keep the 1/6, and then we have the power rule applied to x to the 6th. Now this will be the derivative power rule, right? So 6 times x to the 5th. Okay, so what I have done is take the derivative of this big F, and once we simplify it, by canceling that factor of 6, we should get x to the 5th, which is what we started with back here. These agree, so we're happy. And if you were doing a problem like this on Hawks, for example, it might ask you to type something like this into the box. Okay, let's do another example. So suppose we have a function big G of x that's supposed to be the indefinite integral of 8x to the 5th dx. Take a minute and see if you can figure out what to do with this one. Okay, so first, looking at the function inside the integral sign, you can see that there's multiplication of the constant 8 by x to the 5th, and that is the outermost operation. We'll get to the power rule here in a moment. The first step is simply to hop the 8 times outside the integral symbol. So that is from the antiderivative constant multiple rule, which says that the antiderivative of a times stuff is constant a times the antiderivative of the stuff. Now we need to work on this, but that should be familiar. As a matter of fact, we did that up here. So what I can do is write 8 times and replace the antiderivative of x to the fifth with what we just figured out, 1 over 6 times x to the sixth plus c. Now at this point I'm going to do a couple of things. So thing number one, I'm going to make this c1. And now I'm going to clean up a little bit and explain something about constants of integration. First, I can distribute the multiplication by 8, and so I get 8 times 1/6 times x to the sixth plus 8 times c1. Eight times 1/6 simplifies to, well, 8 over 6, which you can simplify to 4 over 3 times x to the sixth. Now, remember what this c1 is. It's an unspecified constant that comes into play because of the fact that the derivative of stuff plus a constant is just the derivative of the stuff, that the plus constant contributes plus nothing. So when you go backwards from the function to an antiderivative, you have to allow for different possibilities for an added constant on the end. But 8 times an unknown constant is just another unknown constant. So we may as well just write C2 here and just let C2 equal 8C1. The convention that you will see for most antiderivative calculations is to wait till the last step to insert the constant of integration. So what you would normally see is something like this. So let me redo this. Let me do this in this color. So again, I'm going to start with the antiderivative written in definite integral notation like that. The first step would be to hop the multiplication by 8 outside the antiderivative, then to use the antiderivative power rule on power x to the fifth there to get 1/6 x to the sixth, and recognize that this is one antiderivative of 8x to the fifth. And then to make it general, we leave room for an added constant that would be specified by some other piece of information. So again, we end up with 4/3 x to the sixth plus c. And again, this is the answer that we are looking for. Let me see here. Here it is. Here it is the way we did it the first time. And here it is again. Another thing that you can do with this, so let me put in here another way to work, is to look at this 8x to the fifth and think, okay, what kind of thing would I need in a function so that its derivative would have an 8x to the fifth in it? Okay, well, in order to get an x to the fifth out of the derivative of something, I need to have an x to the sixth. So what I can do is try, well, what if I tried g of x equals x to the sixth? So then g prime of x would be 6x to the fifth. Well, that's kind of getting there. I mean, the x to the fifths match up. But to get the 8, yeah, something's wrong here. So I need need to correct. So let's try again. I need to think, what factor do I need to insert right there so that it'll be something that I can then simplify with this 6 and end up with an 8. So in other words, what times 6 equals 8? Well, as a matter of fact, let me just say, all right, so z times 6 equals 8, and I got to solve for z, 8/6. So if I let g of x be 8/6 x to the 6th, then g prime of x will be 8/6 times 6x to the 5th, and that leaves us with just 8x to the 5th once those 6's cancel. Okay, so this is another way to approach these polynomial problems. Um, I find it easy enough to just use the rules, but some students like this kind of um, constructive method where you get part of the answer and then you try a few things and make corrections until you get it to work. At any rate, this is the answer that we're looking for apart from a plus c. And so again, let's just put the plus c in. And you can see that other than the fact that I haven't simplified the 8/6, this is the same thing that we had from before. Okay, so that's a couple of different ways to get the antiderivative. I'll go ahead and write it again, 3/4 x to the 6th plus c. Here's a more, well, it's just a longer polynomial problem. So suppose that big H of p is the antiderivative of 8p to the 5th plus 6p to the 4th plus 3p minus 6. And if you'll notice that the dx, where I'd been having dx, I now have dp. And that's because the independent variable in this problem is p rather than x. Okay, so let's work this one out. Now remember we had this antiderivative sum difference rule, that the antiderivative of a left plus or minus a right, well, let me go ahead and write it with a dp, is, well, you do the antiderivative of the left, let me put parentheses in the right place, antiderivative of the left, and add or subtract the antiderivative of the right. Now I've written it as a rule here for just 2 terms, but it actually works for any number of terms. So in particular, the antiderivative of all of these things added and subtracted together is, well, we work out this first thing. In fact, let me put in the big box here. So we'll do the antiderivative of the first thing, then add in the antiderivative of the second thing, then antiderivative of the next thing, that's 3p, and then minus the antiderivative of the last thing. Okay, now we just need to handle each of these terms. The first term should be familiar. The antiderivative of 8p to the 5th is basically the same thing we did up here. It's just that instead of an x like we had in this example, we'll have a p in this example. So h of p starts with, and I'll copy the 4/3 p to the 6th from above. Now, you may be wondering, what about the plus c? Well, like I said, there's this convention that when you're doing antiderivatives, you can wait and just add one unspecified constant at the very end. If you put in a plus c for each one of these terms, then at the end you'll have, well, c1 plus c2 plus c3 plus c4. You'll be adding up a bunch of unspecified constants. And, well, I mean, a bunch of unspecified constants added together is another unspecified constant. So you may as well just wait till the end to write the plus c. Okay, so we'll leave it as 4/3 p to the 6th for now. Now we need to do the antiderivative of the second term. So take a minute and think about what that should be. Okay, you keep the 6 and multiply by 1/5 p to the 5th. That's the antiderivative power rule applied to p to the 4th. And then we keep the factor of 6. Now we need to do the next one. This one may throw you for a little bit of a loop. Just remember that if there's no exponent, what exponent could I put right here? I could put a 1. So try the antiderivative of 3p to the 1. Okay, so again, we keep multiplication by 3. We apply the antiderivative power rule to p to the 1 to get 1/2 p to the 2. Yeah, you got to keep this straight. The derivative power rule takes you down a degree. The antiderivative power rule takes you up a degree. Minus. Now this one might really throw you for a loop. What do you do if there's no p, if it's just the antiderivative of 6? Okay, well, here's something to think about. So suppose that I have a little f that's equal to 6, and I want big F prime of x to be equal to 6. Well, if f prime is 6, that means that the f has tangent lines that all have the same slope. That should start to sound familiar. The kind of function that has that property is a linear function. And the derivative of a linear function is just the slope. So you can see here that 6x is the antiderivative of 6. Well, you could put in a plus c. So that means that over here, I keep the factor of 6, and I just have a p. So I have a linear term here whose derivative is that 6. Now, just because sometimes you'll see this in integral tables, if you see an integral sign with nothing there, and then the variable, that is meant to indicate that you have an integral of just 1. And the antiderivative of 1 is just the variable. So it's this sort of funny looking notation that you'll sometimes see. And again, what it's telling you is that if you have the antiderivative of a constant function, well, the antiderivative of a constant function is a linear function. And the constant is its slope. Now, a couple of things also to look at. This term is degree 5. Its antiderivative is a degree higher, degree 6. This term is degree 4. Its antiderivative is a notch higher, degree 5. This term is degree 1. Its antiderivative is a notch higher, degree 2. This is a degree 0 term, a constant term, and its antiderivative is degree 1. So the degree goes up a notch for the antiderivative power rule. And finally, since now we've finished dealing with all of those integral signs, we can put in the constant of integration. And, we can clean this up a little bit and do h of p equals 4/3 p to the 6th plus 6/5 p to the 5th plus 3/2 p squared minus 6p plus c. Now, if you wanted to check this, how would you do it? Okay, again, to check, take the derivative and see if you get, well, what should you expect to get? You should expect to get this thing that was inside the integration symbol. So you should get the 8p to the 5th plus 6p to the 4th plus 3p minus 6. Okay, well, let's take the derivative h prime of p and see what we get. So this should be familiar. We've been doing derivatives of polynomials for a while now. 4/3 times 6p to the 5th plus 6/5 times 5p to the 4th plus 3/2 times 2p minus 6 plus 0. And usually we don't even bother to write the plus 0. And again, remember what c is. It's some unspecified constant. And if you clean up the derivative, well, there's not a whole lot we can do here, but well, yeah, we can. We can cancel a factor of 3. That leaves us with 8. We can cancel a factor of 5 there. And we can cancel a factor of 2 here. And sure enough, 8p to the 5th plus 6p to the 4th plus 3p minus 6. And that checks out. That is indeed the thing inside the integral symbol that we started with. So that is the antiderivative of this polynomial. I'll show you a couple of examples with the exponential rule. So first, this is, well, it should be the easiest one. Antiderivative of e to the x dx. We're asked for a function whose derivative is e to the x. Well, remember, e to the x is the amazing indestructible function. The derivative of e to the x is e to the x. That means the antiderivative of e to the x is also e to the x, except that we should put in a plus c. So there you go. That's the basic antiderivative involving e to the x. Now, I did give this rule in a previous video, that the antiderivative of e to the ax is 1 over a e to the ax plus c. If you want, you can use this rule with, well, what would you use for a? I mean, there's nothing right there. What would you use for a? You'd use a equals 1. Because if you stick multiplication by 1 right here, that doesn't change the function. It just puts in 1 times. And if you work it out, you'll see that that's That's what this rule gives you if you use a equal to 1. So that's one of these that's so easy it's hard. Okay. Let's try this one. Give that one a try. Okay, we want the indefinite integral, of e to the 5x dx. Remember, this is the antiderivative rule that we have. So we would use this rule with a equal to what? 5. Right? We're going to match that 5 up with the a. So that means g of x is 1 over 5 e to the 5x, and since that's the last of it, we can add the constant plus c. Again, to check this, we'll take the derivative and see if it takes us back to the thing that was inside the integral symbol. Okay, g prime of x is we keep multiplication by 1/5. Right, we keep multiplication by 1/5. Then the derivative of e to the stuff is e to the stuff, but we have to put in a chain rule factor that's the derivative of the stuff, and the derivative of 5x is 5. And if you really want, the derivative of plus a constant contributes plus 0. But often we don't even bother writing the plus 0. And as I demonstrated before, the point of this 1/5 is it corrects for the chain rule. And we are left with g prime of x equals e to the 5x. And sure enough, this is exactly what was inside the integral symbol up here. And just to make it clear, that's the answer that we're looking for. Okay, let's try this one. H of x is the indefinite integral of 6 times e to the 5x. Take a moment and try to do this one. Okay, now you can see again there's an exponential component, but we can't forget that there's actually another operation, multiplication by the constant 6. So before we start dealing with the e, we'll keep multiplication by 6. Now this should be familiar. As a matter of fact, we did this in the previous example. So 6 times 1/5 e to the 5x. Now that we're finished with all of the antiderivative stuff, finally I'll add the plus c. Now we can clean this up a little bit. H of x equals, put the 6 over 1, multiply the fractions together, 6/5 e to the 5x plus c. And again, to check, you take the derivative of big H. And you get 6/5 times e to the stuff, so e to the 5x, times the derivative of the stuff, times 5, and then plus 0 for the plus c. The factors of 5 cancel, and we're left with h prime of x equals 6e to the 5x. And that agrees with what was inside the integral symbol. And again, just to make clear, this expression for h is the answer that the problem is looking for. Okay, take a moment and try to work out this example. That's the antiderivative, or indefinite integral, of 6e to the 5z minus 3e to the minus 4z. And the dz here is because the independent variable for this function is z instead of x. Okay, so let's take a look at this. Again, look for the outermost operation, and you'll see that it's that subtraction. There are e's floating around, but we'll get to them in a moment. Remember, we have this rule that the antiderivative of a left minus a right is the antiderivative of the left minus the antiderivative of the right. The antiderivative of the left, other than being z instead of x, this is exactly the same function that we were dealing with in this previous example. So the antiderivative should be simply a matter of looking at this and writing z instead of x. So, okay, r of x is, and again, to go through this kind of quickly, we keep the 6 because it's multiplied, and then the antiderivative of e to the 5z is 1/5 e to the 5z. And again, I'll hold the plus constant plus c until the very end. Now we subtract. This has the same structure as the part we just did. It's just instead of a 6, we have a 3, and instead of a 5, we have a -4. So here we go. We keep the factor of 3, and then the antiderivative rule for e to the -4z would be 1 over -4 e to the -4z. And now I'll add a constant, plus c. The only thing left to do now is a little bit of cleanup. Oops. I just realized I've been writing r of x. I should be writing r of z. Here we go, r of z. Well, we already know how to simplify this. We just did that. So 6/5 e to the 5z minus, well, actually over here, we can combine the fractions. We can do, let me do this in that color. We can do a double negative simplification and put a plus here. That'll become plus 3/4 times e to the -4z plus a constant. Now let's check. So remember, this is the answer that we're supposed to find. If we take the derivative of this, we should get back to the stuff that was inside the integral symbol. So let's check. R prime of z is I'll do this part first. We keep the 6/5 times. Derivative of e to stuff is e to stuff. But then the derivative of the stuff for the chain rule, so that gives us times 5, plus I keep multiplication by 3/4. Derivative of e to the stuff is e to the stuff, so e to the negative 4z. And then we have to multiply by the derivative of the stuff, that's the chain rule, and the derivative of negative 4z is negative 4. Then the derivative of c is 0. That's added on, and generally we don't even bother to write it. Now if we clean this up, r prime of z is, well, in this first cluster of factors, we can simplify the 5 and the 5 in the denominator to leave 6 e to the 5z. In the second cluster of factors, we can cancel a 4 in the denominator with that 4 on the outside, but then we're left with a negative. So we've got one negative factor in this cluster. So instead of plus, I have to write minus. And so that leaves 3e to the negative 4z. And sure enough, this agrees with what was there inside the integral symbol, 6e to the 5z minus 3e to the negative 4z. Okay, so this checks out. And again, this is the answer that we're looking for.